In this podcast, we're going to look at horizontal asymptotes and limits as x goes to positive or negative infinity. So a horizontal line is a horizontal asymptote to a function if the function gets infinitely close to the line as x increases or decreases without bounds. So to find a horizontal asymptote, we must determine the value a function approaches as x goes to positive and negative infinity. So what do limits have to do with horizontal asymptotes? Well, key idea, the limit of the function as x goes to positive or negative infinity is the horizontal asymptote. For functions that have a horizontal asymptote, the horizontal asymptote equals the limit as x approaches positive or negative infinity. This isn't in your notes. Please write that down. Actually, anything that I have handwritten in here in this particular podcast, I'd like you to write down. All right, so we're going to be taking limits as x goes to positive or negative infinity and looking to see if we have a horizontal asymptote. If we get a finite number as the limit, then our function has a horizontal asymptote. So if the line y equals b, the line y equals b is a horizontal asymptote of the graph of a function y equals f of x. If either the limit of f of x as x approaches infinity equals b, or the limit of f of x as x approaches negative infinity equals b. If the limit of a function approaches a finite value as x approaches positive or negative infinity, then the limit of the function is also the value of a horizontal asymptote. In your notes, make sure it's written somewhere. The limit equals the horizontal asymptote. And it can be as x goes to infinity, as x goes to negative infinity, or as x goes to positive and negative infinity. In other words, it could be as x increases, as x decreases, or whether or not x increases or decreases, we have the same horizontal asymptote. Right? So some functions have a horizontal asymptote as x approaches infinity. Some have a horizontal asymptote as x approaches negative infinity, and some have a horizontal asymptote for both as x approaches both positive and negative infinity. Sorry about my voice. Keep coughing. All right, so we're going to look at an analytic approach and properties of limits as x approaches positive and negative infinity. So when a limit goes to infinity, we're looking for any horizontal asymptotes, and a number of things can happen. All right, so here we have the limit of x squared as x approaches infinity. All right, and we do know as x increases, y is going to keep increasing without bounds. All right, so that limit is infinity. That doesn't exist. Here, the limit of 3x plus 5 divided by 6x plus 7. All right, so both 3x plus 5 and 6x plus 7 are approaching infinity. That's actually an indeterminate limit because it doesn't tell us anything. All right, and finally, we have the limit of the square root of 2x squared minus 5 minus x as x approaches infinity. And both 2x squared minus 5 and x are approaching infinity as x approaches infinity. That's also an indeterminate limit. It doesn't tell us anything. Infinity minus infinity, what would that be? 0? Not necessarily. All right, so here, the last two, where we have both the numerator and denominator going to infinity, and where we have the difference and both are going to infinity, those are indeterminate limits. Right? They don't tell us anything. Not all infinities are the same. Right? So we're going to learn some algebraic, some analytic techniques to find limits as x approaches infinity. We've looked at numerical and graphical and some properties, and we used the sandwich squeeze theorem. Now let's learn some analytic. All right, so consider the limit of x cubed divided by x squared as x approaches infinity. So the numerator is going to infinity, the denominator is going to infinity. Right? This is an indeterminate limit. Is the limit 1? Well, it is not. And if you say 1, based on that, I'll be kind of sad. Reduce the rational function before substituting, right? Because that limit is not 1. In calculus, we're going to divide each term by the highest power of x and then take the limit. Now, in a case like this, yes, we could reduce, but we're going to have other cases where we can't reduce. So I'm going to show you the technique with this particular one, even though we could reduce. All right, so we have the limit as x approaches infinity of x cubed divided by x squared. We're going to divide everything by the highest power of x. The highest power of x is x cubed. Right? So we'll divide everything by x cubed. So that's going to give us the limit. Notice I'm still writing limit until we finish substituting or evaluating. We keep limit. So the limit as x approaches infinity, x cubed divided by x cubed all over x squared divided by x cubed. Everybody gets divided by the highest power, right? So remember, if we have a constant over x or a constant over x to any power, that's going to be 0, right? Because the numerator is growing without bounds. All right, so let's reduce here. All right, so x cubed divided by x cubed, that'd be 1. And then x squared divided by x cubed, that would be 1 over x. But of course, we're not done yet, right? We got to simplify that, right? So that's the same as, actually, I did something bad. I dropped the words limit. Shame on me. We're not done. Until we're done, word limit has to be up there. Otherwise, we have what's called a linkage error, right? And we're claiming that this could be the value of the function. The limit, remember, is what it's approaching, whether or not the value exists, right? So 1 divided by 1 over x. And now we could simplify that. So that's going to be the limit as x approaches infinity of 1 times, and we take the reciprocal, so 1 divided by 1 over x is the same as 1 times x. And now I can drop the words limit because we're done calculating. It's x. All right, so now x, the limit as x approaches infinity of x, that's infinity, right? That grows without bounds. So this particular function will grow without bounds. We could have also reduced in this case, but we're not going to always be able to reduce. So I did want to show you the technique. We're going to use this technique, dividing by the highest power of x, in all the problems in this particular podcast. And I do want you to show your work on these. All right, make sure you show the property. All right, so we want the limit as x approaches infinity of 2x minus 1 divided by x plus 1. All right, this is an indeterminate form. We're going to divide all terms by the highest power of x. Right, and we're going to use this for evaluating limits of rational functions as x approaches positive or negative infinity. Do not use this technique if x is approaching a finite value. Only for positive or negative infinity. All right? And if we get 1 over x, right, we know that's 0. If we get x over a constant, that would be growing without bounds. Or x to any power over a constant would be growing without bounds. And that would be does not exist. All right? So I think 2x plus 1 divided by x plus 1. Is that on the next slide? Yeah, it's over here. Let's do it. 2x minus 1. This one is 2x minus 1. All right, so we'll say this one when I get to it in a few slides, all right? Since I have it twice. But let's use this technique for the following. All right, so here we can see all three methods. All right, so here we see graphically, right? It appears from our graph, we have a horizontal asymptote right here at 1. So y equals 1 is a horizontal asymptote. Let's look at our table of values here. All right, so if we look from the left-hand side, the right-hand side is first. If we look from the right-hand side, all right, the limit as x approaches 1 from the right-hand side is 1. So this would be the limit as x approaches this one was as x approaches, I have infinity over there. Sorry, infinity, not 1. as x approaches infinity. Does that look like 1? The limit's 1. I'm looking at the values of the function rather than x. Here we've got 0, 50, negative 50, 150, right? So, and I have my value going the wrong direction. We've done so many tables where our value was in the middle there, and we're looking from the left and the right. We're going to infinity and negative infinity. I need to go this direction, all right? So, and there is no limit from the right and left. Let me just fix that. So the limit as x approaches positive infinity of our function here, we'll just put f of x, is 1. Notice it's getting closer and closer to 1. And we go this direction, the limit as x approaches negative infinity, because we're looking over here at the x's. Don't ask me why. I was reading backwards. Decided to read right to left. Is also 1. All right, so as x is approaching infinity and negative infinity, from our table, our limit appears to be 1. From our graph, our limit appears to be 1. Now let's find it analytically. All right, so we're going to divide by the highest power of x. In this case, the highest power equals x. All right, so we're going to have the limit as x approaches infinity of x divided by x plus 1 divided by x divided by x divided by x. All right, so now we'll simplify that. I think I can write one more time. Equals the limit as x approaches infinity. So x over x, that's 1. And then we have 1 over x. And then we have x over x, which is just 1. X divided by x. All right, so now let's calculate that out. All right, so the limit of 1 is 1. 1 over x, that's going to be, that limit is 0. Right? So notice I dropped the limit now because I'm no longer, now I'm actually calculating it out. Right? We're doing the final calculation here. Right? And then the limit of 1 is 1. So now in this case we have a constant. And it's 1. And if the limit as x approaches positive or negative infinity is a constant, that constant is our horizontal asymptote. So here are 3 different ways we've calculated out the horizontal asymptote, and it's clearly 1. Right? Let's do some more. Finding the limits as x approaches positive and negative infinity. Let's find some horizontal asymptotes. All right, so here, numerator and denominator, we saw this problem earlier. They're both going to infinity. That's an indeterminate form. To resolve the problem, you can divide both the numerator and the denominator by x. After dividing, the limit may be evaluated as shown. By the way, there's no reason to show this is the indeterminate limit, infinity over infinity, right? If you have x, if you have x raised to a power and constants, and you're approaching infinity and negative infinity, you just right away use the dividing power. There's no reason to do infinity over infinity. You're just going to divide by the highest power of x. Right? So highest power of x here is just x. So we'll divide everybody by x. So we have the limit as x approaches infinity, 3x divided by x plus 5 divided by x divided by, board is looking a little funky today, 6x divided by x plus 7 divided by x, which is the limit as x approaches infinity. 3x divided by x is going to be 3. Can't reduce that any further. 6x divided by x is going to be a 6. And can't reduce that any further. All right, so that's going to be, now we're calculating limit, and so now I'm going to drop it. I've done the simplifying, so I can take the limit, we're just find the limit, now I can drop the limit. All right, so the limit of 3 is 3. The limit of 5 divided by x, that's 0. The limit of 6 is 6. And the limit as x approaches infinity of 7 over x, that's going to be 0. So we have 3 divided by 6, or 1/2. Right, and so that's our limit. Not only is that our limit, but y equals 1/2 is a horizontal asymptote. And make sure you're filling in your notes as you go along. Right? Right, so we're just going to show the property dividing by the highest power of x for all these problems. And let's look at the next one. All right, so let's find this limit. This is the one on the other page a little while ago. All right, so the highest power of x here is x. I swear the rest of them will all be x. So we have the limit as x approaches infinity. 2x divided by x minus 1 divided by x, all divided by x divided by x plus 1 divided by x equals the limit as x approaches infinity. 2x divided by x is 2. Can't simplify the 1 over x. X divided by x, of course, is 1. You can't simplify the rest. But now we can calculate. So we have 2 minus 0 divided by 1 plus 0, which is 2, which matches our graph. So the line y equals 2 is a horizontal asymptote to the right. By the way, by taking the limit as x approaches negative infinity, we would also get y equals 2. Right? You have the exact same thing with just a negative on your infinity. Nothing else would change. Right? Because this is a horizontal left. Right? So I think it's one of our easiest topics so far. Right, so let's find the limit. Right, so we're going to divide by the highest power of x. Which is x to the 5th. Right, so we have the limit. X approaches infinity. 2x to the 5th divided by x to the 5th plus x to the 4th divided by x to the 5th minus x squared divided by, come on, x to the 5th plus 1 divided by x to the 5th, all divided by 3x cubed divided by x to the 5th minus 5x divided by x to the 5th plus 7 divided by x to the 5th. It's going to give us the limit. Divided by x to the 5th, that's going to be a 2. And then we'll have a 1 over x and a 1 over x cubed. Right? I'm just reducing these. Can't reduce this one at all. And then this would be a 3 over x squared minus a 5 over x to the, calculate it out as soon as, there we go, the rest of the problem decides to appear. All right, so the limit of 2 is 2. And then 1 over x is 0. And so is 1 over x cubed. And so is 1 over x to the 5th. In the denominator, 3 over x squared is 0. So is 5 over x to the 4th, and so is 7 over x to the 5th. Anybody who's got an x, no matter what power it is, in the denominator is going to 0. So we've got 2 in the numerator, 0 in the denominator. Does not exist. Right? In this case, I believe we're approaching infinity, right? Because we're going, it's going to be increasing, because we're approaching positive infinity, right? But just fine, right? Does not exist. Our limit here does not exist. We have no horizontal asymptotes. We don't even have a slant asymptote in this case, because x to the 5th is, the exponent is 2 higher, not just 1. So no kind of horizontal, no kind of slant, right? And the limit doesn't exist. Right? And that's all there is to this one. Let's look at this one. Oh, now we have a radical. What do? We got to just be thinking here. So the square root of x squared would be x. So if I want to divide by x, I need to divide by under the radical. So we're dividing under the square root here. right? So if I really want to divide by x, I have to divide by square root of x squared. I'm going to write the other direction, actually. So, and I'm going to write want to divide by, you should probably put this in your notes. We want to divide by x for the radical and this is a square root, so I'll just draw the square root sign there. All right, so for the square root, we have to divide by x squared. If we want to divide, in this case, we're going to want to divide by x squared. If we want to divide by x squared, we're going to have to divide by x to the fourth. All right? So we're going to divide everybody by x to the fourth, because x to the fourth is our highest power, right? So notice that, and actually I should put a radical here. So make sure that's under the radical. All right, so if we're dividing by x squared, we're dividing, oops, they're stuck. We're dividing by square root of x to the fourth. All right, so we have the limit as x approaches infinity, 4x squared divided by x squared plus 5x divided by x squared minus 6 divided by x squared, all divided by square root 9x to the fourth divided by x to the fourth. It's under the radical. I'll just make it bigger. And then minus 5 divided by x to the fourth. Now don't get confused, not under the radical. So x divided by x squared, because he's not under the radical. Oh, that just looks terrible. X divided by x squared. All right, so it's only if you're under the radical, not just because you're in the denominator. All right, let's simplify this. Limit as x approaches infinity. 4x squared divided by x squared, that's going to be 4. Plus, we're going to end up with a 5 over x and a 6 over x squared divided by a square root of 9 minus 5 over x to the fourth. That's all under the radical. I'll just make it bigger. And that is not x times 4. That's x to the fourth. Let's make that exponent a little smaller. And then this would be plus 1 over x. All right, so that's going to be a 4 plus a 0 minus a 0. I've got a square root of 9 minus 0 plus 0. Right, so that's going to be 4 and the square root of 9, oops, which is 3. So I'm thinking ahead. I did not mean to write that. 4/3. Right, so 4/3 is our limit here. And we're done. By the way, don't just assume, however, that that would have been 4/3 just because it's the square root of 9. Right? We'll see some problems where it won't work out quite that way, right? When it's written a little bit differently and maybe things are moved around a little bit. Right? But if we divide by the highest power of x, we won't go wrong. Right? And all right, maybe this took a little space, but was it difficult? No. So justify with your work. All right, so a comparison of 3 rational functions here. I know this one's in your notes, as well as some of those other ones. All right, so we're going to divide by the highest power of x. And all of these. All right, so we have the limit as x approaches infinity of 2x divided by x squared plus 5 divided by x squared, all divided by 3x squared divided by x squared plus 1 divided by x squared. So that's going to be the limit as x approaches infinity, all reduced 2 over x plus 5 over x squared, all divided by 3 plus 1 over x squared. And that's going to be a 0 plus a 0 divided by a 3 plus a 0. That's a 0, right? So this does have a horizontal asymptote. That's going to be at y equals 0, right? Let's look at this one, right? So we have the limit as x approaches infinity 2x squared, we're dividing everybody by x squared plus 5 divided by x squared, all divided by 3x squared divided by x squared plus 1 divided by x squared. So that's going to be the limit as x approaches infinity. That's going to be a 2 plus a 5 divided by x squared and a 3 plus 1 divided by x squared. So that's going to be a 2 plus a 0 divided by a 3 plus a 0. That's 2/3. Again, this one has a horizontal asymptote. And that horizontal asymptote is y equals 2/3. Let's look at the last one. All right, so we have the limit as x approaches infinity. 2x cubed divided by, we're dividing by x cubed, that's the highest power. X cubed plus 5 divided by x cubed, all divided by 3x squared, I'm going to put this in, divided by x cubes. Well, it's going to expand my board, that's what it's going to do. Divided by x cubed plus 1 divided by x cubed. And that's going to be the limit. Oh, I don't know how that happens. That's happened several times, and I in no way was near that button. The limit as x approaches infinity, that's going to be a 2 plus 5 divided by x cubed all over. That's going to be a 3 divided by x. Notice I'm simplifying, and then I'm dropping limit and calculating out the limit. Right? And this is a 1 divided by x cubed. So do follow these steps, right? Because right now I'm finding the limit, right? And this value doesn't become the limit until I've simplified. Now my last step, it will be the limit, and I can drop that limit. It's equal to 2 plus 0 divided by 0 plus 0. This one does not exist, and we have no horizontal asymptote. Our function is growing without bounds. All right, so there, we've calculated out 3, and 2 of them had horizontal asymptotes. And they're all a little bit different, right? One was 0, one was 2/3, and one didn't have one. Oh, and that's the end of my lesson. All right, so I actually was under 30 minutes. All right, so now I have some problems for you. Okay, easy cheesy, lemon squeezy. All right, so you could find the limit. Some of them are going to positive infinity, some are going to negative infinity. Be kind of careful on that. This one down here, the last one, a little tricky. And show all your steps, and don't forget square root of x squared, that's x. All right, bye for now.